something is pulling planets at the edge of the solar system, and we can't see it. Not a theory, not speculation, mathematics. The orbits of distant objects don't match what gravity alone predicts. They're clustered, tilted, moving in patterns that require an explanation physics can measure, but telescopes can't find. A force is acting on them. Something massive, something dark, something that's been there for billions of years, shaping the outer solar system while remaining invisible to every instrument we've pointed at the sky. This isn't the first time we've searched for hidden planets. Neptune was discovered this way. Its gravity disturbed Uranus before anyone saw it. But this object, if it exists, is different. It's 5 to 10 times Earth's mass, orbiting hundreds of times farther than Neptune, so distant that sunlight reaching it is less than 1/10,000th the intensity we experience on Earth. A world that could orbit for thousands of years without ever coming close enough to reflect light we could detect. If it's real, it means the solar system we thought we understood is incomplete, that for 50 years we've been mapping a structure with a missing piece, that gravity has been writing a signature across the outer reaches that we've only just learned to read. And if it's not real, if the math is wrong, then something else is bending those orbits, something we haven't even considered. This is the story of how mathematics sees what telescopes can't, how orbital mechanics becomes archaeology, how prediction becomes search, and why the most important question might not be where this planet is, but what it means that we can predict something massive and still fail to find it. For most of human history, we knew 6 planets, the ones visible to the naked eye: Mercury, Venus, Mars, Jupiter, Saturn, and Earth. Then, in 1781, William Herschel discovered Uranus, not by prediction, by accident. He was mapping stars and found one that moved. Decades later, astronomers noticed Uranus wasn't moving the way it should. Its orbit wobbled. Something unseen was pulling it. In 1846, mathematicians calculated where that something should be. And when telescopes pointed to that exact location, they found Neptune. The discovery of Neptune proved something profound. Mathematics could reveal worlds before light did, that gravity writes predictions into orbital mechanics that telescopes only confirm later. But the method has limits. In the late 1800s, astronomers predicted another planet, Vulcan, to explain Mercury's orbit. Telescopes searched for decades. It was never found, because it didn't exist. Einstein's relativity explained Mercury without needing a hidden planet, which raises the question, when orbits don't match predictions, are we discovering planets, or discovering that our models are incomplete? Today, the same mathematics that found Neptune is pointing to something new, a super-Earth in the outer solar system, massive enough to tilt orbits, distant enough to remain invisible. But this time, the prediction isn't unanimous. Some models require it, others don't. The orbits are real. The disturbance is measurable. But whether that disturbance comes from a planet or from something else we haven't considered remains unanswered. And the search begins with objects we didn't even know existed 20 years ago. Beyond Neptune lies the Kuiper Belt, a region of icy bodies left over from the solar system's formation. Thousands of objects orbit there. Most follow predictable paths: circular, stable, distributed randomly across the plane of the solar system. That's what gravitational models predict when planets form and clear their neighborhoods. Randomness, not patterns. But in the early 2000s, astronomers began finding objects that didn't fit. Not Kuiper Belt objects, trans-Neptunian objects, dwarf planets like Sedna, orbits so elongated they spend thousands of years beyond Neptune's influence. then swing inward for brief passages near the Sun. And their orbits weren't random. They were aligned. In 2014, astronomers Chad Trujillo and Scott Shepard published a paper noting something unusual. 6 trans-Neptunian objects with perihelia, closest approach to the Sun, aligned in the same direction. Not approximately, precisely, as if something was organizing them. The probability of this happening by chance? Less than 1%. 2 years later, Konstantin Batygin and Mike Brown analyzed the data further. They found the orbits weren't just aligned in direction. They were tilted at the same angle relative to the solar system's plane. All 6, orbiting in a narrow cone of space, as if shepherded by an unseen force. When objects orbit randomly, their orientations distribute evenly. Over millions of years, gravitational interactions with known planets, Jupiter, Saturn, Uranus, Neptune, should scramble any patterns. The fact that these orbits remain aligned means something is actively maintaining them, something massive enough that its gravity dominates the outer solar system, something we haven't accounted for. Batygin and Brown ran simulations, thousands of them, in models without an additional planet. The clustering disappeared within a few million years. In models with a super-Earth, 5 to 10 times Earth's mass, orbiting at 400 to 800 astronomical units, the clustering persisted. The orbits stayed aligned. The tilts remained stable. The math worked. But math is an observation. These aren't small asteroids. Sedna is roughly 1,000 kilometers across. 2012 VP-113, another aligned object, has a perihelion beyond 80 Australian dollars, farther than any known planet ever reaches. These are worlds, and their orbits are being shaped by something we can't see. Either we're missing a planet massive enough to organize the outer solar system, or we're missing something fundamental about how gravity works at these distances. The alignment isn't drifting. It's stable, which means whatever is causing it has been there for billions of years, shaping orbits since the solar system formed, pulling on objects we've only just discovered. Something is organizing these orbits. The clustering is too precise to be chance. The tilts are too stable to be temporary. Either there's a planet we haven't found, or there's a force we haven't considered. And the only way to know is to search, not for the planet directly, but for more objects. Because every new trans-Neptunian object with an aligned orbit strengthens the prediction, and every one that doesn't weakens it. But the search for Planet 9 isn't new. It's the latest chapter in a 200-year history of predicting planets that don't exist. And the method that found Neptune also predicted a planet that was never there. In the mid-1800s, astronomers noticed something wrong with Mercury. Its orbit precessed. The point of closest approach to the Sun shifted slightly with each orbit. This is normal. Jupiter and Venus pull on Mercury, causing the shift. But when astronomers calculated how much precession those planets should cause, the number didn't match observations. Mercury was precessing 43 arcseconds per century more than predicted. 43 arcseconds. A tiny amount. Roughly the width of a human hair seen from across a football field. But in celestial mechanics, tiny discrepancies mean something is missing from the model. And the solution seemed obvious. Another planet, orbiting closer to the Sun than Mercury. A world so close to the Sun's glare that telescopes couldn't see it. Astronomers named it Vulcan before it was even found. For decades, astronomers searched for Vulcan. During solar eclipses, when the Sun's light was blocked, telescopes scanned the region near the Sun for anything moving. Some claimed to see it. Flickers of light, transits across the Sun's disk. But nothing confirmed. No orbit established. No mass calculated. Just hints. shadows, possibilities. In 1915, the search ended, not because Vulcan was found, because Einstein published his theory of general relativity. Gravity, Einstein showed, isn't just a force. It's curvature of space-time. And near massive objects like the Sun, space-time curves enough to affect orbits in ways Newton's laws don't predict. When astronomers recalculated Mercury's orbit using relativity, the extra precession appeared naturally. Exactly 43 arcseconds per century. Vulcan wasn't needed. It had never existed. Vulcan was predicted using the same method that found Neptune. Orbital mechanics, gravitational disturbances, mathematical precision. And it was wrong. Not because the math was flawed, the precession was real, but because the model was incomplete. The disturbance came from relativity, not from a planet. Which means when we see orbital anomalies, we have two possible explanations: a hidden mass or incomplete physics. Planet 9's prediction is stronger than Vulcan's ever was. Multiple objects, consistent clustering, statistical significance beyond 1% chance. But stronger isn't certain. And the history of Vulcan is a reminder that mathematics can predict things that don't exist. That our models reflect what we understand, not necessarily what's real. That sometimes the most elegant explanation isn't a new planet. It's a better theory of gravity. Some researchers propose that the clustering isn't caused by a single planet. It's caused by the combined gravitational influence of many smaller objects in the Kuiper Belt. A collective effect, like a flock of birds moving as one without a leader. Simulations show it's possible. Not likely, but possible. Others suggest observational bias. We find aligned orbits because we're looking in aligned directions. That the pattern is artifact, not evidence. The difference between Neptune and Vulcan was observation. Neptune was predicted, then seen. Vulcan was predicted, then never seen, then explained away. Planet 9 sits in the middle. Predicted but not yet seen. And the longer it remains unseen, the more the prediction resembles Vulcan. A mathematical ghost. A pattern in the data that points to something missing, but not necessarily something real. The question isn't just whether Planet 9 exists. It's whether we trust the method that found Neptune enough to keep searching, even after the method also invented Vulcan. Whether orbital mechanics is a map to hidden worlds, or a mirror reflecting the limits of our models. And whether absence of evidence is evidence of absence, or just evidence that we haven't looked in the right place yet. But if Planet 9 does exist, it's not hiding in the inner solar system where Vulcan was supposed to be. It's hiding in the darkest, coldest, most distant reaches we've ever tried to observe. And finding something that far requires understanding just how dark and cold the outer solar system actually is. At Earth, sunlight delivers about 1,360 watts per square meter. Bright enough to see clearly, warm enough to sustain life. At Neptune's distance, 30 astronomical units, that drops to 1.5 watts per square meter. Dim, but still detectable. At 400 astronomical units, where Planet 9 is predicted to orbit, sunlight delivers less than 0.008 watts per square meter. That's 1/10,000th Earth's intensity. 1/400th Neptune's. A planet at that distance doesn't shine. It reflects. And what it reflects depends on how much light reaches it and how much its surface absorbs. If Planet 9 has an albedo similar to Neptune, about 40% reflectivity, it would appear as a faint magnitude 24 or fainter. That's roughly 160,000 times dimmer than the faintest stars visible to the naked eye, detectable by the largest telescopes, but only barely, and only if you know exactly where to point. The problem is scale. The predicted region where Planet 9 might orbit covers thousands of square degrees of sky. The Vera Rubin Observatory, once operational, will survey the entire visible sky repeatedly. But even with automated detection systems, distinguishing a faint, slow-moving planet from background stars, distant galaxies, and instrumental artifacts requires years of comparison. A planet at $500 moves less than 1 degree per decade. You don't see it move in real time. You detect its motion by comparing images taken years apart. And there's another complication: orbital uncertainty. Badigian and Brown's models constrain Planet 9's orbit to a broad region, but not a specific location. It could be near perihelion, closest approach to the Sun, where it's brightest and fastest moving. Or it could be near aphelion, farthest point, where it's dimmest and slowest. If it's near aphelion, it might be beyond the detection threshold of even the most sensitive surveys. Temperature adds another layer of difficulty. At $400, a planet receives almost no heat from the Sun. Its surface temperature would be around 40 Kelvin, minus 233 degrees Celsius, cold enough that any atmosphere would freeze onto the surface, cold enough that infrared emission, heat radiation, is negligible. Most planets are easier to detect in infrared because they emit their own heat. Jupiter, for example, radiates more energy than it receives from the Sun. But Planet 9, if it exists, is likely a cold, dead world, radiating almost nothing, reflecting almost nothing, invisible to infrared surveys that have mapped most of the sky. This is the edge of visibility, the point where detection becomes archaeology, where finding a planet means not seeing it directly, but inferring its presence from the absence of light, from the bending of orbits, from the statistical clustering of objects that shouldn't cluster, from mathematics that sees what telescopes can't. Neptune was found within a year of its prediction. Vulcan was searched for over 50 years and never found. Planet 9 has been predicted since 2016. Observatories have scanned portions of the predicted region. No confirmed detection, which means either the planet is in a region we haven't surveyed, or it's fainter than models predict, or it doesn't exist. And the longer the search continues without result, the more the prediction starts to resemble Vulcan, a planet that made sense mathematically, but wasn't real. But the absence of direct detection doesn't mean the search has failed, because the method for finding Planet 9 isn't pointing telescopes at empty sky and hoping. It's finding more trans-Neptunian objects and seeing if their orbits match the pattern. And that search is producing results, just not the ones anyone expected. Since 2016, dozens of new trans-Neptunian objects have been discovered. Some have orbits that match Planet 9's predicted influence. Others don't. The clustering that Badigian and Brown identified in 6 objects has been tested with more data, and the results are ambiguous. Some studies confirm the clustering. The alignment persists. The tilts remain consistent. Statistical tests show the probability of random chance is still low. But other studies suggest the pattern might be observational bias. Telescopes survey certain regions of sky more thoroughly than others. Objects with aligned orbits might appear clustered simply because those are the regions where surveys are most sensitive. In other words, we find aligned orbits because we're looking where aligned orbits would be visible, not because something is actually aligning them. This is a fundamental problem in astronomy. You can't observe what you don't look at. And if your surveys are biased toward certain regions of sky, your data will reflect that bias. Correcting for bias requires modeling survey completeness, understanding not just what you found, but what you could have found if it were there. And those models are uncertain. In 2021, A team led by Kevin Napier analyzed the same trans-Neptunian objects using updated survey data and found that the clustering was statistically consistent with random chance. Not definitely random, but not definitely clustered either. The pattern could be real, or it could be an artifact of where telescopes have pointed. The data doesn't eliminate Planet 9, but it doesn't confirm it either. This is the uncomfortable truth about pattern recognition in sparse data. With 6 objects, you can calculate probabilities. With 20 objects, you can refine them. But sparse data doesn't give you certainty. It gives you likelihood, and likelihood can shift depending on how you analyze it. Badigian and Brown's original analysis used one set of assumptions. Napier's analysis used different assumptions. Both are scientifically valid. Both produce different conclusions. The clustering might be real. It might not. And until we have enough trans-Neptunian objects to map the outer solar system comprehensively, hundreds, not dozens, the question remains open, which means the prediction of Planet 9 sits in a strange epistemic space, strong enough to justify search efforts, not strong enough to declare discovery imminent. A hypothesis supported by some data, contradicted by other data, and dependent on assumptions that can't yet be tested conclusively. This isn't a failure of science. It's how science works at the edge of the known universe, where data is sparse, observations are difficult, and patterns emerge that might be signal or might be noise. The history of astronomy is filled with patterns that turned out to be real, and patterns that turned out to be illusions. Canals on Mars. Vulcan, the planet X that was supposed to explain Pluto's orbit before better measurements showed Pluto's mass was too small to perturb anything. Planet 9 might join Neptune as a triumph of prediction, or it might join Vulcan as a cautionary tale. And the only way to know is to keep searching, not for the planet directly, but for more objects. Because if the pattern is real, more data will strengthen it. And if the pattern is biased, more data will erase it. Either outcome answers the question, but both require patience. Years of surveys, decades maybe, mapping a region of space so vast and so dark that finding anything requires not just looking, but looking in the right direction at the right time. And that raises the deepest question of all. If a planet orbits for billions of years in the outer darkness, influencing nothing we can see and reflecting light too faint to detect, does it exist in any meaningful sense? Or does existence require observation? These aren't just scientific questions. They're philosophical ones. And Planet 9, whether real or not, forces us to confront them. Assume for a moment that Planet 9 doesn't exist, that the clustering is biased, that the orbits align by chance, that the outer solar system contains no hidden super-Earth. What would that mean? It would mean our models are wrong. Not catastrophically wrong. The physics of gravity hasn't changed, but wrong in the details. Wrong about how trans-Neptunian objects scatter. Wrong about how the Kuiper Belt formed. Wrong about what we should expect to see when we look at the edge of the solar system. And being wrong about the details means rewriting those models, testing new hypotheses, refining our understanding of orbital mechanics in regions where planets are sparse and perturbations are weak. Science doesn't fail when predictions don't come true. It fails when predictions aren't tested. Planet 9 has been tested. The prediction has driven surveys. The hypothesis has been analyzed, refined, debated, and challenged. Whether it's confirmed or refuted, the process has taught us something about trans-Neptunian objects, about observational bias, about how to search for things that might not be there. But there's another possibility. Not that Planet 9 doesn't exist, but that it exists in a form we didn't predict. Not a super-Earth, not a captured rogue planet, but something else. A primordial black hole, perhaps. A tiny singularity with the mass of several Earths, but the size of a grapefruit, orbiting unseen in the outer darkness. Gravitationally identical to a planet, observationally invisible. Some models suggest this is possible. Not likely, but possible. And if true, it would explain why the orbits are disturbed but telescopes find nothing. Or maybe Planet 9 is a planet, but not where models predict. Maybe its orbit is more eccentric. Maybe it's closer to the Sun than expected, but in a region of sky not yet thoroughly surveyed. Maybe it's farther, beyond even the optimistic detection limits. Orbital mechanics constrains where it could be, but doesn't eliminate possibilities. The predicted region is large, the sky is larger, and absence of detection isn't proof of absence. Neptune took 1 year to find after its prediction, but Neptune was close, bright, moving relatively fast. Planet 9, if it exists, is none of those things. It's distant, faint, slow. Finding it might take decades, or it might never be found, not because it doesn't exist, but because it's beyond our ability to detect with current technology. Future observatories, space telescopes, infrared surveys, gravitational wave detectors sensitive enough to map the solar system's mass distribution might reveal it, or they might not. And if they don't, if 50 years pass and no planet is found, and the clustering fades as more data arrives, then Planet 9 joins the long history of objects predicted but never observed. Vulcan, Planet X, the hypothetical moons of Venus, predictions born from data, sustained by mathematics, and eventually abandoned when better explanations emerge. But the search itself matters. The Vera Rubin Observatory will survey the sky, whether Planet 9 exists or not. The data will map the outer solar system in unprecedented detail, and that data will answer questions we haven't even asked yet. About the Kuiper Belt, about trans-Neptunian objects, about how the solar system formed and evolved. Planet 9 is the motivation, but the science extends beyond the prediction. That's how exploration works. You search for one thing and find another. You predict a planet and discover a belt. You look for Vulcan and develop relativity. You model orbits and learn that models are provisional. That prediction is a tool, not a truth. That the universe doesn't owe us answers just because we've asked questions. Planet 9 might be real. It might not. And the uncertainty isn't a flaw in the method. It's a feature of the cosmos. A reminder that the edge of the known universe isn't a boundary, it's a gradient. A region where certainty fades into probability, observation fades into inference, and prediction fades into hope. Where mathematics sees what telescopes can't, but what mathematics sees might not be there. And maybe that's the real discovery. Not the planet, the question, the search, the willingness to look into the darkness and admit we don't know what we'll find, or whether we'll find anything at all. Something is pulling planets at the edge of the solar system. The orbits are real. The clustering is measurable. The disturbance is written into the trajectories of worlds we've only just discovered. But whether that disturbance comes from a planet or from something else remains unknown. The search for Planet 9 has driven a decade of observation, new trans-Neptunian objects, refined orbital models, statistical analyses that test whether patterns are signal or noise. And through it all, one truth has emerged. Prediction is not the same as discovery. Mathematics can point, but only observation confirms. Neptune was predicted and found. Vulcan was predicted and never found. Planet 9 sits between them, strong enough to justify search, not strong enough to declare victory. A hypothesis that makes sense until it doesn't. A pattern that holds until more data arrives and erases it, or strengthens it. The history of astronomy is filled with objects that seemed inevitable until they weren't, and objects that seemed impossible until they were. We thought the solar system ended at Saturn. Then we found Uranus. We thought Uranus was the edge. Then we found Neptune. We thought Neptune defined the outer boundary. Then we found Pluto and the Kuiper Belt and thousands of objects beyond. The edge keeps moving, and every time it moves, we realize how little we actually knew. If Planet 9 exists, it will be found. Maybe next year. Maybe in 30 years. Maybe by a telescope that hasn't been built yet, using a method we haven't invented. Or maybe it won't be found because it doesn't exist, and the disturbance comes from something smaller, or stranger, or more fundamental than a missing planet. But the search doesn't end if Planet 9 is ruled out, because the question isn't really about one planet. It's about whether we understand the solar system we live in, whether the map we've drawn is complete, or whether there are still blank spaces waiting to be filled, whether gravity writes signatures we can read, or whether the patterns we see are reflections of the assumptions we make. The outer solar system is dark, cold, vast. Objects out there move slowly enough that their orbits take millennia to trace. Light from the sun reaches them as faint whispers. Telescopes detect them as dim smudges against an even dimmer background. And somewhere in that darkness, there might be a world 5 to 10 times Earth's mass, orbiting unseen, pulling on objects we've only just begun to catalog. Or there might not be. And maybe the answer to that question matters less than the willingness to ask it. To look into the darkness and wonder what's there. To build models and test them. To predict and search and refine and search again. To admit that the universe is larger than our certainty, stranger than our models, and indifferent to whether we ever find what we're looking for. The solar system we thought we understood might be incomplete, or it might be exactly what we see, and the patterns we detect are illusions born from sparse data and biased surveys. Either way, the search continues, not because discovery is guaranteed, because uncertainty is unbearable, and the only way to resolve it is to keep looking. Something is pulling planets at the edge of the solar system, and whether we ever see it or not, the pull is real. If this changed how you see the difference between prediction and discovery, or what it means to search for something that might not be there, consider subscribing. There are more questions waiting.